Welcome, physics students. Today we're going to look at integration and the chain rule. This is actually going to be our last review video on calculus before we move on to the electricity and magnetism topics of the year. And before we begin, I just want to remind you that the integral of a function is the antiderivative of the function. For example, if I start with a function t to the fourth power and I take the derivative, remember what I do is I bring the 4 to the front and then I subtract 1 from the exponent and I get 4t to the third power. If I add a dt, then if I integrate this, I get back the original function. This is why we call the integral the antiderivative. You follow the process for taking derivative in reverse. And I mention this because in today's topic, we're going to be taking functions like this maybe. Oops. And trying to integrate them. So what you might be tempted to do is add 1 to the exponent to the fourth power and then divide by that 1/4 and all this to the fourth power. And it doesn't work that way, okay? Let me show you why. Remember, derivative, antiderivative when you integrate. So let's start with a function 3t to the fourth plus 1 cubed, So this is what we thought maybe the integral would be with a 1/4 in the front. If we take the derivative of this though, we put the 4 to the front, then we subtract 1 from the exponent, but then we have to multiply by the chain rule the derivative of what's inside here, which is going to be 3 times 3 or 9t, and then subtract 1 from the exponent, plus the derivative of 1, which is 0, so I won't even write that. So all of this is the derivative of that. So if I want to integrate this, I can add a dt, and then all of this integrates to that, because this is the antiderivative of all of this. Okay, so all of this stuff makes for a much more complicated integral. It is necessary in order to integrate to have these terms here. So that's what we're going to look at today. How do you integrate when, see, I knew the answer here, and then I made the derivative, and then I knew, so the integral of that. But what if I don't know this? Then there are techniques for working our way back the antiderivative to get the integral of a function. So you don't have to write this down. It's just sort of a way to prime your mind about how things have to be more complex when we have functions like this that we have to integrate with these various terms here. So I'm just going to work through some examples, showing you techniques through examples. So let's say example 1. Let's see. So here is our problem. We have a velocity function like this. This might be a car or a rocket or something is moving with this velocity. At time 0, you can see we have 0 velocity and then it increases from there. And we want to know how far this object goes from 1 to 3 seconds. So I'll do this just for this one example, the reminder of what an integral is, the concepts behind the integration. So this is my velocity function. If you were to plot this on a calculator, you would get some kind of sharp parabola-looking function. I didn't make it as sharp as it really was because basically I want to, kind of stretch it out so you could see what I'm doing. So what we do is we imagine while this thing is moving, velocity times time is the most basic expression for how far something goes. The meters per second times seconds. The problem is if the velocity is changing, we have to pick a time over which that velocity is roughly constant. So like let's say a trillionth of a second, we've got a little tiny fragment of time here, dt. And for that fragment of time, we could say the object went a certain distance. That's the velocity at that moment times the dt. So this is a real skinny rectangle right here. And so I could say that the dx is v dt. That's the distance it went in that trillionth of a second. This object advanced a certain distance. What's the total distance it went? Meters per second times seconds. Well, what I would do is then take delta x being the sum starting at 1 to 3 seconds of all these tiny displacements over a millionth or trillionth of a second, I said. So the velocity is that function. So there's the velocity times the time. Okay? I'm going to pause the video now to give you a chance to jot this down. Okay, let me continue on here. Make a little space. I'm going to show you two different ways to integrate this. Okay, and one is going to be a longer, more drawn out way that really shows more specifically what's happening, and then there's going to be kind of like a shortcut. Okay, so first thing I'm going to do is, I think it was to the 4th power. So make sure you add that to your notes, the 4th power. The first thing I'm going to do is I'm going to let u equal 2t cubed plus 1. The reason why is I would like to make this of the form like x to the 4th, because I know how to integrate x to the 4th. So if I can eliminate this and simplify it with a new variable, then I can simplify my function. But then I'm getting rid of this, so I have to get rid of all time terms. I got rid of time here, but I still have time here. So in order to get rid of these time terms, I'm going to take the derivative of this. du dt, therefore, is 6t squared. And so what I'm going to do is I'm going to have t squared dt on one side. So I can do that and say, by moving this dt over here, I've got t squared dt over here. And then I'm going to move the 6 to the other side and have 1/6 du. Okay? So now I can get rid of this and the t squared and the dt together. And my delta x function will now be the integral. And the time, we don't have time anymore, so I'm just going to put over u. The variable's a u instead of time. New limits, but I'm not even going to figure them out. I'm going to take this 7, first of all, and leave it out front. In fact, Maybe I'll put it in front of the integral. Might be clearer that way. And then all of this is now u to the fourth by my substitution. And then the t squared times dt, that I figured out is 1/6 du. So I'm going to go like this. I'm going to put du here, and then the 1/6 sort of just hanging out right there like that. So the constants come together as 7/6. And then now I have a very simple integral. U to the fourth du, I can use the power rule because it's just a very simple in terms of u. So what I do is I add 1 to the exponent, making u to the fifth, and then dividing by 5 over our limits of u. So I have 7/30 with all the constants in the front. And then what I'm going to do is, now that I used u to allow me to integrate, I don't need it anymore. It's just like a temporary variable to allow you to integrate. So I put back what u is, 2t cubed plus 1. And then recall that the limits are from 1 to 3 seconds. That's how far, I want to know how far it goes between 1 second and 3 seconds. And now I just plug in my limits. So I have 7/30, 2, 3 cubed plus 1. Oops. I lost the fifth power here again, so make sure you add that fifth power to the fifth power. Okay, so I put in 3 in for one limit, and then I subtract off 1 for the other limit. And then I won't even evaluate it because, you know, you just from there punch it in on your calculator and get an answer. So that's how you do it. I'm going to pause the video now to give you a chance to catch up if you need to catch up with that problem. Okay, so that's the longer way of doing it. We try and simplify this into some very simple power integral. And the way we achieve that is we let all this be a new variable u. That gets rid of this. And then we also have to get rid of this too because we need all time out of the variable. By the way, this means that this would not work if, for example, this was to the third power. Because when we get to this point, we have t squared dt that we can substitute out. And so what that would do here is leave an extra t, and t would not be eliminated. So we couldn't integrate this way. If it has to be 1 less than the power here, otherwise this technique doesn't work. Okay? Brings a little side topic. Derivatives are always easier to do than integrals. If you take your time, there's always a way to follow the rules of derivatives to get an answer. Not always the case with integration. You can easily write functions for which there's no integral, and then the only way to integrate it is with a computer and brute calculations. All right, well, this was a pretty long process. What I'm going to do now is show you a shorter way, a quicker way to get this answer. Okay, so what I'm going to do is erase up to here to give myself some room. Okay. So here's a shortcut. So let me just rewrite what my integral is. Delta x equals the integral from 1 to 3 seconds So what I'm going to do is, rather than do a u substitution, what I'm going to do is take the derivative of what's inside the parentheses here. So du dt here is 6t squared plus the derivative of 1, which is 0. So I know that if, oops, I forgot to change this back to squared. I apologize for the other error here. So I can see that if I had a 6t squared dt and this, I would basically have the derivative of my function, and I could just go back and take an antiderivative. So what I could do is bring the 7 out here, and I'm going to leave a little space over here. I'm going to write my integral from 1 to 3 seconds. And I'm just going to put the 6t squared, well, maybe I'll put it all together. 2t cubed plus 1 to the 4th power, 6t squared dt. Because that's what I need. I need a 6t squared and the dt in order to integrate this and create an antiderivative. And you might be saying, well, how could you just insert a 6 there? Haven't I changed the function? It used to be a 7. I'm adding an extra 6. I did. And here's how I can fix that. I can put a 1/6 over here. See that? And the function's the same function. Extra 6 and a 1/6 together go to 1, giving me my original function. Now I know, because this is the derivative of what's inside, that I can just take the antiderivative. And all of this is like my du, and this is my u, which means I can just add 1 to the exponent, the 7/6 here, which makes it to the 5th power, and I'm going to leave a little space here, 2t cubed plus 1 to the 5th power. I add 1 to the exponent and then divide by the new exponent. And then I evaluate that from 1 to 3 seconds. In other words, 7 over 30, 2, 3 cubed plus 1 to the 5th power minus 2, 1 cubed plus 1 to the 5th power. And then I evaluate that and get my answer. So you see, a little bit quicker, rather than writing those 3 lines, let u be this, and then du dt, and then so on and so forth, I just kind of quickly do it and save myself a little time. Okay? I'm going to pause now to give you a chance to write down this shortcut technique. Okay, so I'm just going to do a few more examples using the shortcut technique. Okay. Let's see, what did I pick here? 3. Okay. So I can say delta x will be the integral from 0 to 4 seconds of my function 3e negative 1/4 t dt. So I can call this u. And so du dt is negative 1/4. So that means if I do this, I'm going to leave a little space here and say e to the negative 1/4 t times negative 1/4 dt. What I would have is basically this being, all of this being du for u being negative 1/4 t. So what I have is e to the u du right here. Now, I added this negative 1/4 when it didn't exist in the original function. So what I'm going to do is I'm going to add negative 4/1 here. And I've basically now made the function the same as what I started with. So this now integrates to negative 12 e to the negative 1/4 t. Again, because all of this is du and this is u. So e to the u du just integrates to e to the u. And then I put in my limits 0 to 4 seconds, and I plug in my limits and solve. Okay? So there's the second example. Okay? And I'll pause the video now to give you a chance to copy this down if you haven't already. Okay, let's look at another example. Okay, so okay, so there's our velocity function, and we're looking for how far this thing goes from 0 to 5 seconds. So once again, delta x will be the integral from 0 to 5 seconds of this 5 e to the minus 2t cubed t squared dt. I moved the t squared over here. Maybe it'll make it a little easier to work with later. So again, we could do a u substitution. Let this be equal to u, take the derivative, solve for t squared dt, and work that way. But again, we're just going to do it with this little shortcut. The derivative of this du dt will be negative 6t squared. So I could rewrite this integral with the 5 out here, and I'm going to leave a little space here, 0 to 5 seconds of e to the negative 2t cubed. And I see I got to add a negative 6 over here so that all of this here will be du of our function. So we'll have e to the u du here. Okay? But I can't just put a negative 6 in there. unless I put a negative 1/6 over here. All right, so I haven't changed the function by adding that -6. So now the integral of the exponential, e to the u du, is just e to the u. So I have -5/6 here. And e to the u is our integral. And I evaluate that from 0 to 5 seconds. I plug in the numbers, punch the calculator, and I get my answer. Okay? All right, I'm going to pause the video now to give you a chance to jot this down. Okay, let's do one more example. Okay. Let's see. So there's the question. This object is got a velocity that oscillates between +3 and -3. So it's doing this simple harmonic motion, back and forth, forward and backwards, oscillating like this. Okay? So the displacement for 0 to 3 seconds for reasons I explained right at the beginning, it's the integral of v dt. Okay? Now, if I had sine of t dt, then that integrates to negative cosine. Okay? But I don't. I've got a function inside the... So this is like u, and I could do a u substitution, and then when I take the derivative of u with respect to time, I've got 5 pi over 2. Oops. Times the 1, right? And then t to the 0. So times 1 t to the 0, it's just 5 pi over 2. Plus the derivative of pi over 2 plus 0, right? So it's just that. So I can rewrite this integral knowing that I have to have an extra 5 pi over 2 with the dt in order for myself to go back to the original function, taking the antiderivative. So I'll put the 3 here, and I'm going to leave a space here. And I'm integrating from 0 to 3 seconds. So I add that extra 5 pi over 2. In order to not change the value of the function, I've got to add over here a 2 over 5 pi. Right? And then this cross out. So I haven't changed the function, but inside the integral I have sine to the u du, which then integrates to 6 over 5 pi. So as I said, the integral of sine is negative cosine, okay, so there, integral negative cosine, and then I evaluate from 0 to 3 seconds. And so what I can do is just plug in those limits, punch the buttons on my calculator, and I'll have the answer. Okay. So I'll pause the video here to give you a chance to catch up. Okay, so that is integration in the chain rule. I showed you the first example. I showed you the logic behind what an integral is. It's adding up the v dt's, this tiny displacements for a millionth of a second, from one point to another. So I explained the logic again and the thinking behind an integral. Then I showed the first example done out with a u substitution, which you're always welcome to do if you don't mind the extra writing. I showed that same example with this little shortcut technique, adding a number here and the reciprocal there to have function u du, and then you can integrate. And it's a little bit quicker doing that sort of shortcut technique. All right, so that's it for calculus review videos. I'll see you in the next video where we start beginning our study of electricity and magnetism.